Other factors to consider are quality of roads, availability of fresh water, electric power, and local infrastructure. The pond itself is simply an earthen basin constructed partly by excavating soils from the bottom and partly by building up the perimeter levees. The water depth should be a minimum of 3 feet in the shallow end and slope to a depth of 5 feet to 6 feet in the deep end. The U.S. Soil Conservation Service offers local assistance in soil analysis and pond design. Although a wide variety of earth-moving equipment can be used to construct ponds, the most precise and efficient is the laser-controlled dirt buggy used routinely for land leveling applications. The water system for the ponds consists of a pump station, a water supply canal or pipeline, inlet and outlet control structures, and a drainage ditch. The size of the drainage culvert used for the outlet control structure of the shrimp pond is designed much larger than that for a typical fish pond. This is necessary to allow complete draining within about 8 hours to facilitate harvest. A concrete harvest box, designed to accept a submersible harvest pump, is generally incorporated into the outlet control structure of the pond. To avoid recycling of wastewater from the ponds, the discharge end of the drainage ditch should be positioned as far as possible from the pump station. The pump station is usually located at the shoreline for lifting water into the supply canal. A variety of pumps is used for this purpose, including axial flow, centrifugal, and submersible. In cases where the depth of water is shallow near the pump station, then dredging or an extended inlet pipeline is required. Provisions must be made in the water supply system for filtration to remove predators such as fish and crabs. Most farms simply install mesh bags or screen panels with 0.4 to 0.5 millimeter mesh to filter water just before it enters the pond. However, in order to minimize damage to native organisms, it may be necessary for new facilities to place screens before the pump or to install self-cleaning screens that return filtered organisms back to the bay. Management systems for commercial grow-out of post-larval shrimp to marketable size represent a continuum from natural ecosystems yielding very low production to highly controlled artificial environments yielding very high production. For ease of discussion, these continuum will be divided into 3 commonly used categories: extensive, semi-extensive, and intensive. Extensive systems are semi-natural systems that utilize little or no artificial feeds. Because shrimp must subsist solely on natural foods within the pond, stocking densities are low, generally less than 20,000 per acre. Consequently, extensive management is considered appropriate only when costs of acquiring land and constructing ponds are low. In the United States, this applies primarily to existing brackish water impoundments that are poorly designed for shrimp culture. Semi-intensive systems utilize moderate stocking densities in the range of 40,000 to 60,000 per acre. Pelleted feeds are offered to supplement natural food organisms, and limited daily water exchange is provided to improve water quality. Production rates generally average about 1,000 pounds per acre. Most of the farms in Latin America and several in the United States are managed semi-intensively. Intensive systems utilize stocking densities in the range of 100,000 to 150,000 per acre. At this density, the shrimp quickly consume the natural food organisms in the pond. As a result, a relatively expensive, nutritionally complete ration must be used. Water quality is maintained through aeration and relatively high rates of water exchange. Production rates of 3,000 to 4,000 pounds per acre are common. Intensive management of shrimp ponds, first practiced in Taiwan, is now practiced worldwide, and it is the most common system in the United States. Here are the procedures for intensive pond management. The pond should be filled with filtered water during April, about 2 weeks before stocking. A combination of inorganic and organic fertilizer is added to the pond to stimulate the phytoplankton and zooplankton populations in the pond. A typical fertilization rate is about 50 pounds of urea, 10 pounds of superphosphate, and 200 pounds of cottonseed meal per acre. However, rates vary depending on the natural fertility of local water and soils. Half this rate should be applied again at weekly intervals to sustain the plankton bloom for at least 2 weeks after stocking. Before purchasing post larvae from an out-of-state hatchery, check regulatory requirements about certification of disease-free post larvae. Some hatcheries may be unable to provide required documents certifying that post larvae are free of non-indigenous viruses, bacteria, and parasites. At stocking, post-larval shrimp are received from the hatchery in oxygenated plastic bags inside styrofoam boxes. Each shipping bag normally contains 10,000 to 20,000 post larvae, or PLs. It is critical that the PLs be gradually adjusted or acclimated to the water quality in the pond before stocking. This involves opening the bags, providing aeration, and then gradually adding pond water to the shipping water until differences in temperature are less than 2 degrees centigrade, differences in salinity are less than 2 parts per thousand, and differences in pH are less than 1/2 a unit. Many farms combine the shipping bags destined for a single pond into an acclimation tank beside the pond. This tank is aerated, gradually filled with pond water, then drained into the pond. To conform to the number of PLs being stocked, it's important to perform an adequate estimate of PLs in the shipment. This is accomplished by drawing several well-mixed samples of the total volume, counting the live PLs in each sample, then extrapolating these samples to the entire volume. Although a well-fertilized pond with a rich plankton bloom will satisfy the nutritional needs of newly stocked PLs for several days, most intensive farms begin offering small quantities of feed immediately to train the shrimp to eat an artificial diet. Initially, shrimp should be offered a well-balanced 45 to 50% protein fine crumble. As they grow, this changes to a 40% protein coarse crumble and ultimately to a 35 to 40% protein pellet. Feeding the appropriate amount is complicated by the inability to see the shrimp eating, unlike catfish and trout. During the first month, shrimp are fed based on assumed survival and growth rates. The amount of feed offered during this period is small, and the consequences of incorrect assumptions are relatively insignificant. However, at the start of the second month, it is important to adjust daily feeding amounts based on the actual consumption of the shrimp. This can be done by placing about 1% of each feeding amount on each of several feeding trays. These are analogous to dinner plates made out of netting that is loaded with the feed allotment, lowered to the bottom, then checked about 2 hours later to evaluate consumption. If all the feed on each tray is gone, then the feeding rate is increased by 5 to 10%. The addition of feed and fertilizer to the pond greatly increases nutrient levels that stimulate dense populations of bacteria, phytoplankton, and zooplankton. These biological changes lead to dramatic changes in the water chemistry. The environment within a high-density shrimp pond, therefore, can degrade quickly from that of a natural estuarine habitat to that of a sewage treatment pond. During early morning hours, especially in the hot summer months, the high organic load in intensive ponds frequently leads to oxygen shortages, that is, levels less than 3 parts per million. Mechanical aeration is required to sustain suitable levels of dissolved oxygen. A variety of aquaculture aerators are available, including paddle wheels, aspirating jets, and air injection systems. Paddle wheels are the most common aerators. Usually 3 to 4 horsepower of aeration is used per acre of pond area. To evaluate water quality in intensive ponds, it is necessary to routinely monitor several parameters, including temperature, salinity, dissolved oxygen, pH, ammonia, nitrite, and hydrogen sulfide. Many of the parameters are relatively constant in pond systems and can be measured on a weekly basis. However, dissolved oxygen fluctuates erratically and should be checked at least once each day at dawn. Hydrogen sulfide is difficult to measure chemically at the parts per billion level. As an alternative, the pond manager should monitor the pond bottom for accumulation of black sludge with a characteristic rotten egg odor. Most problems with deteriorating water quality can be solved by early detection and use of increased aeration and water exchange. Water exchange rates are usually increased at monthly intervals from 5% in the first month, 10% in the second, 15 to 20% in the third, and 20 to 30% from the fourth until harvest. Seldom is it cost-effective to use chemicals or antibiotics for water treatment in ponds. Shrimp are susceptible to a variety of viral, bacterial, and parasitic diseases, but disease outbreaks are generally a secondary effect of stress associated with poor water quality or nutrition. The most effective method of preventing disease is to manage water quality to prevent stressful episodes such as low dissolved oxygen, and to offer appropriate quantities of a well-balanced feed. If sick or dying shrimp are observed in the pond, arrange to send samples to your Extension fish disease specialist for diagnosis. Without an accurate diagnosis, the appropriate treatment method cannot be determined. If ponds are constructed with a sloped bottom and a large drain, they can be harvested by draining the shrimp out with the water. This procedure involves slowly lowering the water level by 50% during the day before the harvest. Then, on harvest day, the remaining 50% is released quickly to drain the pond within about 8 hours. Shrimp generally hold back until the final 6 to 12 inches of water leaves the pond. Then they swim out through the drain pipe. Most American farms minimize harvesting labor by using a submersible pump designed originally for live harvesting of trout. This allows them to lift the live shrimp directly to a dewatering tower, after which they tumble into an ice bath. The shrimp are then conveyed to a scale for weighing in 50-pound lots. Finally, they must be packed between alternating layers of ice to hold their temperature near freezing. Because shrimp have a limited shelf life on ice, arrangements are generally made to have them processed and frozen at a shrimp processing plant. The typical processing procedure involves deheading, grading into size classes, weighing, packing into 5-pound waxed cardboard boxes, then freezing with a thin glaze. Marketing is one of the most overlooked yet essential aspects of shrimp farming. If shrimp are sold as a standard commodity item, they will compete directly with inexpensive imports. The successful farmer will seek innovative niche markets that offer a premium for shrimp produced or packed in a specific way. For example, rather than a 5-pound cardboard box designed for wholesale distribution, the farmer might arrange to have his product packed in a 1-pound transparent vacuum pack for retail distribution. Shrimp farming in the United States is a new business without a track record of success. Although America offers a large and immediate market, international competition is strong. The successful shrimp farmer must combine production and marketing skills while continually taking advantage of technological innovations. The future is bright for those who can produce seafood efficiently because wild-caught supplies are reaching their limit.